Welcome everyone. I am Bidisha. Today I am going to talk about our work, a hierarchical VAE for calibrating attributes while generating text using normalizing flow. This is a joint work with Mohit Agarwal and Niloy Ganguly, and we are from Department of Computer Science and Engineering, Indian Institute of Technology, Kharagpur. To start with, calibrating attributes at text generation is a very important problem where it actually means that we can start with any sentence given certain attribute of interest, like here the attribute is sentiment and the sentence talks about a food review, and our objective is to flip the sentiment. This kind of transfer is called attribute transfer or style transfer. Another way of transferring is that we can start with a given sentence and incrementally change the attribute value and generate sentences accordingly. So this is more fine-grained transfer, but also we need to make sure that during this fine-grained transfer, the context should be there. It should not be dropped. Attribute transfer existing approaches rely sometimes on entangled generative space. That is, start with a sentence, encode it to a representation space, try to generate some sentence, then uses a classifier to figure out that what attribute value it bears. If it does not belong to the one of our interest, we just propagate this signal back to the encoding representation space, and we part up the representation again and again and keeps on generating the sentence until and unless we generate a candidate which has, say, negative sentiment. This kind of approach gives emphasis on content preservation, and hence it just explored the neighborhood of the original representation set. Discovery of target sentence thus depends on multiple trial at the time of generation, and the model cannot generate attribute flip sentences if training sentence bearing different attribute values situated at distant representation space. Another approach deals with disentangled generative space, that is, starting with a sentence, it first generates a representation, which then it split to two different independent representation space. At the time of training, it tries to make sure there is no mutual information between these two, that is content and attribute, and try to generate a sentence of our interest by assigning some appropriate representation value on this attribute space. And then we can generate, say here, a negative sentiment sentence, keeping the content intact. However, there are certain issues with disentangled representation space as well, because in the process, we actually lose the interdependency between context and attributes. So that results sometimes in drop of important information. For example, straightforward simple sentences like the first one, it is able to flip the attribute successfully. But for some complex sentence where the attribute space change actually needs to update like several other words in the sentence, it drops few of the important words. Now, this kind of approach, if we want to extend for fine-grained transfer, this problem becomes worse. It drops the information. Not only that, some sentences are completely not related, and sometimes it is unnatural as well. So our objective is to do attribute transfer, preserving the context, and also to able to do fine-grained transfer successfully. For that, we propose our architecture, which is a hierarchical VAE-based architecture, where we preserve both the entangled representation and disentangled representation in two different hierarchies. So in the top hierarchy, we are doing all attribute regulation, and from there, the signal propagates to the lower layer where we are doing the sentence generation. And this transformation between these two spaces is actually reversible, so that we can preserve the interdependency between the attribute and context space, which are disentangled in the upper layer. The hierarchical encoding works like this. We start with a sentence encoder, where we provide a sentence generates representation from BART, then we convert it to a continuous representation space. So this continuous representation is actually an entangled representation. From that representation, we transform it to another representation space, which we call feature representation space, using a normalizing flow. This feature representation space we will use for several attribute supervision and disentangle constraint imposition. In the right, we are showing how this transformation are working. So basically all the dimension of ZS are actually goes through a set of transformation, and this information are channelized to the last dimension of the ZF that we actually preserve for the attribute ZF. And this transformed information along with the original ZS are actually contributing to the rest of the dimensions that we preserve for context. Once we have all the information in the last dimension, we are applying some attribute regulation, that is some feature supervision there, where using some attribute decoder, we try to predict the attribute value, and then the signal goes back to the transformation encoder. That increases the correlation between the continuous representation space and discrete attribute values. Now, modeling the attribute in a single dimension actually helps in fine-grained transfer, because we can now interpolate on a single dimension. So for example, here is a Yelp sentiment dataset where we are interpolating from the minimum minus 3.5 to plus 4.5, which were actually derived from the after the training is done. So hierarchical decoding works like this. Other than this attribute decoding, the upper layer decoder actually do the reverse transformation so that these ZF can be mapped again to ZS. So we do a set of inverse operations where we are starting with the ZA, it goes through some operations, and then we map its effect to all the dimension of ZS. Similarly, for the context, we also do a set of transformation, and then we try to restore back the effect of ZF on the dimensions of ZS. For training, we are doing a phase-wise training. First, we train the lower layer with sentence reconstruction loss and minimizing the variational loss, and in the upper layer, we are minimizing the attribute reconstruction loss, and we are maximizing the log probability density for the flow, that is the transformation network parameters. And then also we are doing variational loss minimization between the ZF and the prior. So the prior is a standard normal distribution, which is a factored distribution, and imposing that kind of a prior on ZF actually enforce the disentanglement over its dimensions. For experiment, we are using sentiment and formality, and we are using these three different kind of algorithms to compare our performances with. In the first experiment, we do attribute transfer, and for sentiment, we are showing the results. So we do an unconditional transfer where we start with a random ZF and just assign our attribute representation to ZA and generate sentences. We are seeing that we are able to generate sentences with high accuracy. At the same time, some other alternatives are also achieving the same, that is DA. However, when we go for attribute flipping, that is preserving the content, just flipping the attribute, we can see that we are doing much better than the disentanglement based methods, which are highlighted in red. So they are not able to generate like related content. In those cases, they fail to achieve the purpose, and hence their accuracy also drops. We further experiment with fine-grained transfer. That is, we just incrementally change the ZA, which we are showing the degree of transfer in the x-axis, and in the y-axis we report attribute polarity. That is the average score provided by 3 human annotators, which denotes that how much a particular sentence entails the particular attribute. Here the attribute is hatred, and we can see as we go to the left, it is becoming the value of AP is very low. That means we are not generating any sentence which is having hateful content. And in the right, we are seeing that we are able to generate like more hateful content. So from left to right, there is a monotonic pattern, increasing pattern, whereas for other alternatives, there is no such pattern. And in terms of relatedness, we are also generating the sentences which are having like higher relatedness with the original one. This is a qualitative example where we start with a sentence which has certain words like retard and considered as a hateful sentence. If we do the transition using control gen, which is a disentanglement generative space, we are generating sentences which are not related to the original one. For entangle gen, we are always generating some counter speech, whereas in case of ours, we are gradually able to actually remove the hateful words and introduce some politeness to it. In conclusion, we propose a hierarchical architecture for fine-grained attribute regulated text generation. It helps in content preservation and fine-grained transfer. In future, we would like to extend the framework for updating multiple attributes simultaneously. Thank you. Code and data will be available here.